Good afternoon. Today we'll continue with our discussion of C amplifiers and BJT applications. So last class we covered C amplifier with a fixed base bias. Let's see, not that. And we stopped right here. Okay, so we saw how a small AC signal injected into the base, so the input side, resulted in an amplified version of the exact same signal, right? Inverted by 180 degrees. So small input signal in millivolts resulted in a large signal of 4 volts peak to peak, right? Now, I'm going to talk about clipping and distortion. Now, in this circuit, we had a collector resistor and a base resistor, RB. So it was the simplest of biasing circuits, right? Simplest of biasing circuits. So there was no emitter resistor. There's no other coupling capacitors, okay? The purpose of the bias, as stated earlier, is to center the operating point in the middle of the active region. We want it somewhere here. But what happens if the Q point, the initial position of the Q point, instead of being in the center, is either closer to cutoff or towards saturation? Well, if the initial point is towards cutoff, let's say, then when you apply our signal, the positive peak is going to exceed 10 volts, right? So your signal might be somewhere here, and the positive peak would get cut off. Okay. So again, if the operating point due to the DC biasing is closer to cutoff in the load line, the positive peaks of the output signal would get cut off or clipped. Okay. And if the same Q point, instead of being in the center, is somewhere here towards saturation region, well, same thing happens, but this time the negative peaks would get clipped or cut off. Because if your Q point is here, your signal is getting cut off like this. And so the negative portion would get clipped. In both cases, clipping results. And because of clipping, the output waveform looks something like this. Okay, so it's clipped off. So this positive clipping would be a result of the Q point towards cutoff region, and the negative clipping would be due to a result of the Q point bias towards the saturation region. So at least one peak or one half peak would be cut or clipped off. Now, that's distortion, that's clipping, right? A second case occurs when the input signal is large. So the input signal right here is varying between minus 0.4 to plus 0.4 volts peak to peak. In the lab, if you recall, you obtained a 100 millivolt signal from the function generator and you stepped it down by a ratio of 1:10. So you're applying a very small signal into the base of your BJT amplifier. So if the signal is large enough, then it could exceed the DC supply that is being applied. Instead of your V out being 4 volts peak to peak with a DC biasing, it could exceed 10 volts. So the second case is input is large, output will exceed VCC limits. And again, result is clipping. This clipping is known as distortion of the waveform. And in real life, you'd experience a tearing sound coming from your speakers. So if you have ever turned the volume up in any of your audio systems beyond the capabilities of your amplifier or the speaker, then it will sound as if the speaker cone is tearing apart, right? I'm assuming you have at least on one occasion in all these years observed something like that. So what's happening is basically distortion or clipping off the waveform. Okay. Any questions? Right. Okay. So as we were talking about biasing, the purpose of biasing is to position the operating point or the Q point in the middle of the active region. This is by far the simplest of biasing circuits, where you simply apply a resistor at the base and a resistor at the collector. You apply DC voltages, right? But this kind of circuit depends on the value of the beta of the transistor. Okay, so it is dependent on the beta of the transistor. The beta of the transistor, whether it's the same make and model, varies wildly. As an example, the transistor we used in our labs, 2222 or the 3904, can have a beta ranging from about 30, 35 all the way to 200. Okay, so you could have two transistors in your lab kit. Amplifier would work with one of the transistors. If you plug in the second one, it may not work, or it may result in clipping or distortion. Okay, that's a result of the biasing conditions. Okay, the end result of such a bias or a simple biasing circuit, as we are seeing here, is that it is highly dependent on beta. Okay, and of course, to avoid that, there are many other kinds of circuits and many other kinds of biasing configurations that we can use. One of the most common ones and is the self-biasing circuit, or more commonly known as the 4-resistor bias or a voltage divider bias. 4-resistor bias, or even more commonly known as the voltage divider biasing circuit. This is, in fact, the circuit we used in the lab. So once you're done with today's class and you're reviewing this material, you can go back and take a look at the resistors and everything we used for that lab. Okay. All right, so 4-resistor bias. The name is kind of obvious. There are 4 resistors in the circuit, one at each of the BJT terminals, and an additional one, a 4th one at the base. Okay. Also known as the voltage divider bias, because the base resistors R1 and R2 form a voltage divider network. A voltage divider network, recall from circuits 1 or E115, is a series connection of components or a series connection of resistors where you apply one single voltage. The current through those resistors is the same, but the voltage gets divided according to a fraction depending on the ratio of these resistors, right? So we have a voltage divider network, R1 and R2. Obviously, when it's part of the circuit, there's a third terminal in there. So we would say that it's not technically in series, right? But when we analyze the circuit, the effect is the same. Okay. So if you take a look at the circuit, what we want to do is we want to obtain this configuration. We want to have one single base resistor so we can calculate the base current that's going into the transistor, right? Now, this circuit was designed decades ago, right? So the analysis of the circuit has already been done. All we're trying to do here is we're trying to understand the analysis, and we're trying to see how is it that the output is not dependent on the beta of the transistor. Okay, so I'm going to limit our discussion and the equation, the analysis that we see here to make that point or to illustrate that point. All right. In general, if you have a circuit, you're analyzing it as an engineer. If you're looking at a circuit and you wish to analyze, you always have a final goal, right? And you work backwards off of from that final goal. In this case, our goal is to obtain an equation for the output. The output can be in terms of the current, IC, or it could be in terms of the voltage, VC. So collector current or collector voltage. On the input side, we have the base voltage or the base current, IB. So essentially, we want to find an expression for IC in terms of the input IB or the input voltage, VB. That's what we want to do. And then we look at the final equation and try and see if we can minimize the effects of transistor beta on the output current IC. Okay. So if we wish to analyze the circuit, the first step is to find the value of the single base resistor RB. Again, the BJT is not a sentient device. It's not a sentient being, right? If you connect 2 resistors, if you connect 20 resistors, all the base is seeing is one equivalent single resistor, right? And to determine that single equivalent resistor and the single equivalent voltage, we need to determine the Thevenin circuit as seen by the base. So we apply Thevenin theorem on the input side. Okay. The beauty of this circuit is that we can use one single supply, and one single supply biases the collector side, and it also biases the base side of input. Okay. And so by using a voltage divider bias on the input side, we can use the exact same voltage that is on the output. Yes. So the difference between this circuit and the previous one was that we had an RE. Is that the point? Essentially, yes. Yeah, but we also had to have 2 power supplies in that case. So the previous one looked something like this. Remember? So it didn't have an RE, but it had 2 power supplies, one VBB and one VCC. So we had 2 separate power supplies. In this case, we only need one. Only one VCC is required. Right? The voltage divider bias is showing an effective VBB. Again, the previous circuit was this. So, right? It had a collector resistor, it had a base resistor, it had a collector voltage VCC, and it had a base voltage VBB, 2 power supplies. In this case, we don't have to worry about connecting a second power supply on the base side because the voltage divider network itself creates a voltage that needs to be applied from the VCC. And to determine that, we use the Thevenin theorem. Once we apply Thevenin theorem, we can calculate the equivalent resistance as seen from the perspective of the base, as well as the VBB value that we're applying into the base. So the Thevenin network as seen by the base is right here. You have the 2 resistors, you apply VCC between the 2 resistors, and you're taking the output between the terminals A and B. B, A, this would be B. Okay. So you want to calculate Thevenin voltage and Thevenin resistance. V out can be calculated directly by applying the voltage divider equation. So it's a fraction of VCC, which is VCC and R2 over R1 plus R2. And then the total Thevenin resistance is simply R1 in parallel with R2. Voltage source behaves like a short circuit. And so we're trying to find REQ. Voltage is replaced with a short. And that renders R1 in parallel with R2. And that gives me R1, R2 divided by R1 plus R2, which is here. Okay. So once we have that, we plug those values here, and we can calculate what IB, IC are. Okay, to generate these equations, we apply KVL. In this case, we're going to start on the input side, apply KVL on the input side. We apply KVL on the input side, we obtain 1 voltage here, second here, third here, and fourth there. There are 4 voltages on the input side. So we obtain this expression to begin with. Okay. Now, we want to obtain an equation for IC or VCE, right? IC or VCE. Output voltage or output current in terms of the input voltage or input current. So you're going to replace VRB with IB times RB and VRE with IE times RE. So now we have an input current in there. IB is introduced into the equation. We want to obtain IC. So we are going to take IE and we are going to replace it with IC and IB. IE is the sum of IC and IB. IC can be replaced with beta times IB. And so IE is replaced with IB times beta plus 1. Okay. So we plug that into here and rearrange the terms so that we have IB on one side of the equation and the rest on the other side. Once we have that, rearrange the terms again to obtain an expression for IB. And that is the expression we want, right? Because from here we know that beta IB is IC, so we can replace IB with IC, which is what we do here. And that's our final step before we obtain an expression for the output current IC, which is here. Okay. That's our final equation. Okay. IC is equal to VBB minus VBE over RB over beta plus 1 times RE over beta. Now, let's see how this equation works for us, right? Beta is typically large. Let's say even if it's the lowest value that we know of, which is like 35, or let's say even 30. If it's 30, beta plus 1 divided by beta is 31 over 30, approximately equal to 1. If beta is large, like 100 or 200, makes it even smaller. So beta plus 1 over beta would be 201 over 100 or 201 over 100. So this term right here, beta plus 1 over beta, is essentially equal to 1. We don't even have to make an assumption. It's approximately equal to 1. So the effect of beta is minimized, at least as far as that quantity goes. Okay. No need for any assumptions, no need for any values, nothing like that. Beta plus 1 over beta is approximately equal to 1. It doesn't matter what kind of transistor we are using. Make sense to everyone? Right? And so this term reduces to simply, or the denominator simply reduces to RB over beta plus RE. Now here's where the design part comes into the picture. This is RB divided by beta plus RE. As a designer, if we want to minimize the effect of beta on the circuit, on the output, we can choose RB over beta. Sorry, we can choose values for RB and RE such that RB divided by beta is far less than the value of RE. Okay, so we design it such that RB divided by beta is far less than RE. In that case, we can ignore RB over beta, and we can say IC is equal to VBB minus VBE divided by RE. So the effects of beta are minimized. Okay. So in general, transistor current or collector current IC is a function of IB. Beta times IB gives us IC. But by using external components, we can minimize the effect of the individual transistor beta. In this case, the gain of the transistor is gain of the circuit is dependent on the components that we're connecting. And that's how we obtain a beta independent amplifier circuit. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Okay. So beta value, the variation in beta will still affect the circuit, but the effects are minimized. Okay, effects are far minimized. And in the couple of minutes I have left, I want to quickly cover, just in brief, I'm going to introduce the next 4 topics, which is the 4 applications of a BJT. And then next class, we'll look at those in detail. So there's 4 applications of a BJT. The first one is as a large signal amplifier, where we are taking a diode and we are creating a diode thermometer. Okay. The diode voltage change as a function of temperature is a very well-defined linear relationship. And the change the change in diode voltage as a function of change in temperature is in millivolts. Okay, so what we are doing is we're taking that change in millivolts and applying it as an input to the base of the transistor, and we are operating the transistor in the active region. Okay, so the transistor takes that small signal and amplifies it, so we can use that amplified output in like digital readouts to create like temperature and digital thermometers. Do you have a question? The diode is acting as a sensor, actually, not as a voltage. What voltage source? Yes, electrically, if you want to represent it as a voltage source, yes, but it's actually working as a temperature sensor. We'll talk more about this on Wednesday. Right now, I just want to introduce these topics. Okay, LED driver. Oftentimes, we have systems where we use single or multiple LEDs as visual indicators of some function in a system. Most of the time, let's say these are sensor outputs. The sensor outputs are small in voltage and in current and weak in current. So they are not sufficient enough to turn on a LED. LEDs typically require voltages in excess of 1.1 volts and currents in excess of 15 to 20 milliamps. The sensor outputs or controller board outputs sometimes are not sufficient to drive these kind of LEDs. And so we attach a transistor for every LED that we want to use in our system. So the output of a controller board or a sensor would be in millivolts or microamps. That small input signal is applied to the base, and this transistor acts as a digital switch. The transistor turns on, and it connects or it provides a pathway for the 5-volt source or the current to flow through the LED through the transistor. Okay, so that's one other application using as an LED driver. And 2 other applications are pretty similar. You can use it as a battery charger. In the battery charger, again, the level of the battery decides how much the transistor would turn on, or how much current would allow you to flow through the transistor. Simply permits a pathway for the current to flow through the battery, and then it can control the battery charging. And then lastly is a motor driver. This is an interesting application because we have two transistors in there. High current application requirement for a DC motor. So the output of the first transistor feeds into the input of the second transistor, which allows a large amount of current to flow through that DC motor. Okay, and all of this is something we'll look at in our next class. Okay, we'll end class here today, and we'll pick up here again on Wednesday.